and you can tell me if you are seeing what I want you to see. Just a second. Are you seeing my screen?
Yeah. Yes.
And can you see well? Like it's not too small or something like this?
Well, for me it's perfect, but my screen is huge, so not a parameter.
Oh, okay. It's okay.
But I think it's good.
So,
Okay, I think.
okay. So thanks for the special guest today. I think this is something very interesting for us to have. And I prepared this presentation kind of in a short time, so do not expect that much. Like I tried to make it like the most literal that I could to avoid mathematical technicalities and things that people could strange somehow, because I know that in our group we have kind of people working things different. So I wanted to avoid details that would just make things super boring. So I tried to make. I'm gonna try to present this work like in the most conceptual way instead of the mathematical way. So feel free to ask me questions in any sense that you want, but expect something less mathematical here, okay? And I'm going to talk about this work that's kind of recent as a result of a collaboration that I had with Victor Cervantes. With interestingly, it's a guy that works in the department of psychology in the University of USA. So this is what particularly interesting for me because it's an experience that not the usual that we usually have, right? But basically, what we want to do here is to relate measures of contextuality in systems that present this property of cyclicality. So just to start, are you all familiar with cyclic systems? Does anyone have anyone never heard about this? Nine? Okay. I'm not seeing everyone in the screen, so I'm assuming that if I have at least one, it's worth the explanation at some point in more detail. So okay. Okay, so I split this presentation in 4 steps, basically 4 parts, and I'm going to start. I tried to formulate things in a sense that I'll give more the context in which my work fits, like what it's used for, or like where you should expect to see the other literature. So I guess that this is the most important part because the mathematical detail is just kind of a proof of something. So I just wanted to situate you of what we have done here and where you can look up for more details in the proof if you are interested in. But what I want here is mostly to be able to see the physics and not only the mathematical result that we got. So the motivation for this is nothing less than Barbara's work, and this is the work that she had. I'm referencing you for this work, and it's the work that she has on contextuality as a quantum resource. And what we know about this, that contextuality is being explored as a quantum resource in computational and communication tasks, in the sense that its presence is associated to advantages in tasks in comparison to classical counterparts, or as a mean to explain the advantage of quantum computing itself, like the nature of it, and something like in the foundations, and more in the foundation sense. So, for example, we have, in the case of model-based quantum computation, it's a necessary. So, just one thing. What screen are you seeing? The presentation itself, or you're seeing me changing screens the whole time? I'm changing here, but I just want you to see the slides presentation.
We're seeing just the presentation.
Okay. So coming back. Okay, for example, in model-based quantum computing, we can see quantum contextuality as a necessary research to achieve universal computing, but I don't know too much details on this to tell. So perhaps Barbara could say more if you're interested. But I mean, it's just here for you to know. And on the other hand, you can also see the usefulness of quantum contextuality, for example, in the use of generation of random numbers. And here I recall that contextual models are not compatible with that idea of deterministic responses, and this is what we exploit to in the tasks to generate random numbers. And we can also use contextuality to certify that our quantum system is working as expected. Something that we call self-testing. And now, going properly to the work, we need basically two ingredients to understand where this contribution fits in. And the first ingredient of it is the basics of resource theory. And what we in resource theory, we need to start from a set of objects that should be the elements that can contain what we are going to study as a resource. In our case, it's just behaviors, right? And once we have behaviors, we need a manner to relate these behaviors, and this is where enters what we call free operations. These free operations, they propose a form of ordering in our theory. So it defines a pre-ordered structure of the objects, and what we know of these free operations is also from a work of from Barbara's, is that non-contextual wirings are the most general set. I mean, the best set that we have for such operations so far to characterize contextuality theory for the contextuality theory and the resource theory of contextuality, and what these free operations basically do. They basically glue the ideas of preparation and post-processing in the systems. And once we are able to relate these objects that we have, and naturally with these kind of orderings, we will have the objects that cannot have the resource that we are interested in. And these objects are obviously non-contextual behaviors. And finally, the most important part here for the work is the element in the theory that is called the quantifiers, which are just functions mapping objects into real numbers, while preserving this pre-order structure previously established by the free operations. So in other words, these quantifiers are just a proper rule to quantify the resource. And since this quantifier preserve the pre-order structure, by studying them, we can study the structure of the objects themselves. So this kind of completes what I wanted to say about the motivations for the work. So at this point, I don't know if I should pause to make some stops, but here you can ask me something if you want, because I stopped here for the motivation, so I don't know if you're in the same page. So if you want to ask something. It's okay? Can I go? Great. So, okay. So this is just to understand what I want to mean by why we want to study quantifiers. So now I'm going to just situate you on why we use cyclic system for this, and the reason for using them It's just because of their simplicity and because they have very known examples used in applications. And what is good about cyclic systems is that they can be easily defined, of course. And here I'm going to define it in very informal, through the use of very informal sentences, but that are enough for us to understand what they are. So in a cyclic systems, we have a set of measurements in which only pair of measurements can be made together, and each property is measured twice throughout. So jumping directly in the visual form of this, graphically, they can be represented as a cycle or a polygon with measured properties as vertices and joint pairs of measurements as edges. So I took this picture from our book on graph approach that I also recommend you to see. And here, this picture, okay, so this example here with 4 vertices is the famous, represents the famous CHS8 scenario, while this example here, this example here with the 5 vertices represents the KCBS scenario. But you can also find examples in the literature for n equals 3, n equals 6. I mean, n here is supposed to be just the number of vertices in the graph. And you can find physical examples for this 2 in the borders also. Okay, so now our work basically completed what was missing in a conjecture that was present in the literature. And to understand it, I will just give some ideas of the approach that we use. Basically, we have to adopt an approach for contextuality. So the one that we chose to work here is the one that goes by the name of contextuality by default. One of the persons behind this is Victor, that is in the collaboration. And here, okay, in contextuality by default, for those that are not familiar with, we basically try to model systems in which it's a variable that is supposed to give the answer for a given property. I mean, if it's present or not, the variable is represented by the property that it answers, or I mean, it characterizes, and the context in which this variable is measured. And behaviors, are as always represented by just the set of joint distributions within variables sharing the context. And I mean, I guess everyone is familiar here, but as I was saying, behaviors are just the set of joint distributions for each context. And if a behavior is non-contextual, we know that it can be written as originated by a joint probability distribution for all the random variables in the system. So here we can let's say that the P is our non-contextual behavior. So it could be we should be able to write this behavior as originated by the action of a matrix that characterizes the scenario onto this vector that we call a multi-maximal coupling in this approach. But basically should be understood here as just the joint probability distribution of all random variables laid together. Okay, and as always, as a probability distribution, it should be greater than 0, greater or equal than 0, each of its entry, and so this sum to 1. So just to summarize, if we have a non-contextual behavior, we should be able to write it in this form that is in this grid. So, okay, once we have something that is not non-contextual, what would we do? So basically, a non-contextual behavior satisfies conditions that we can enumerate like in the following. So, and if we want to construct something to describe things that are not non-contextual, we are basically relaxing some conditions that I believe that what you are seeing in the screen is the weight of summarized ideas. So essentially, we can say that non-contextual system satisfies these three conditions, and quantifiers are constructed by relaxing at least one of them. So clearly, one should be able to find a joint probability distribution. So that X that I previously mentioned here. So I'm gonna be interchanging the word joint probability and the coupling, but they mean the same thing here. So please, if it gets confused at any point, just stop me, and I can rephrase anything. So okay, if I have something that behavior that's non-contextual, we should be able to find a joint probability distribution, and from that joint probability distribution, the marginals, let's say that the joint probability distributions within context only should agree with what we observe. So with the behavior that we have in hand, of course, and such a joint distribution should also agree with something that we call multimaximality, that is a notion of equality across contexts, that which means like if you have a random variable and it gives information to you of a property that we call Q, and this property can be answered like by measuring two different contexts. Equality here in this multimaximal sense means that we are allowing the variables should be as much equal as they can by the marginals. By the single distributions of themselves. I know that this is kind of very literal, and some mathematical expression here would help, but I don't want to get into that. To not distract you from the main topic. But the idea is basically that we need to find, if we have something that's non-contextual, we need to find a joint probability distribution. We are able to find a joint probability distribution for all the random variables in the system, and if we restrict our attention to the variables sharing a given context, for example, the joint probability distribution for the whole should marginalize the correct joint probability distribution within a context. And if we look for variables that share the property that's being measured, it should be as equal as they can. So if we want to construct a quantifier of something that's that is contextual, we should relax some of at least one of these properties. Here I'm going to talk about the quantifiers that we have in the literature that are known, and in between brackets, so you're going to see what is the condition that they relax. And for example, we have this contextual measure that we call CNT0, that basically measures the maximal degree of violation of an inequality. And basically it violates the conditions 2 and 3 that I mentioned before. And we also have another measure that I'm going to call CNT1, which is basically, that basically is when you want to see the distance of the behavior that you have to a polytope of behaviors with the same observed distributions, but that do not agree with that equality across contexts. And finally, we have CNT2 with the violation that condition 2 that I mentioned before, and which basically tell us about the distance that our contextual behavior is to the polytope of non-contextual behavior themselves. So we have a set, for example, the one way of imagining this, we have the set of joint probability distributions for the whole, and the behaviors that they can generate, and but they cannot generate our contextual behavior, so we take our contextual behavior and look for the distance to the polytope. And this is the interpretation for this from this measure. And we also have a measure in which we can just violate the role of being a proper probability, in the sense that we can recover all the marginals that we want, and we can recover agreement across contexts, but only by allowing the presence of negative masses in the joint probability distributions for the whole system. And we have another measure that I'm going to call CMTF here. Basically, it is allowed to violate any of the conditions before, and basically what we are going to ask for it is that X, that is that coupling that I mentioned, cannot sum to 1, do not need to sum to 1. So basically what I'm saying is that I'm looking now for the portion of my system that can be represented by a non-contextual system beside another contextual system. Like suppose, in other words, so you have, for example, contextual behavior, and you want to try to simulate this or somehow reach this behavior using some system that's classical, for example, and then what you can do with that is just a portion of the behavior that you got, and this measure try to capture this idea. So, okay, now that we know the quantifiers that we have in the literature for quantum contextuality in this approach, I can now state the conjecture itself, and it's quite simple. It basically says that all those measures are proportional within cyclic systems. And okay, and what we know is that 3 of these measures that I mentioned were proven to be proportional to each other in this reference here. That I'm not gonna talk about too much in details, but here's for the ones that are interested. And in this other reference here, one can find the proportionality between CNT2 and CNTF, of the 2 cyclic system also. And okay, so where our contribution enters, and our contribution enters in the sense of we wanted to include the missing part in that relation that was CNT3, and this is the result. So basically what we are saying is that if you have a system that is cyclic of rank n, then its degree of contextuality in the sense prescribed by CNTF is proportional to the degree prescribed by the measure CNT3. And this is supposed to close an understanding of cyclic systems in literature, basically because the most studied quantifiers in the literature are the ones that I mentioned here, although there are other ones with different natures and different motivations. But I mean, I'm going to talk about the details of what we did not consider here in the end, but this is basically the motivations that for those quantifiers that we already know and we have already studied well, the proportionality within cyclic systems is now closed, so we have a good understanding of cyclic systems. And okay, so let's understand our result. I'm going to present here like in a very simple way, also to avoid another confusion and not miss the main point. So this is going to be in a very sketchy way. And okay, so we're going to understand how the proofs go in 4 steps. So okay, we have a contextual behavior of the star that we're going to test for contextuality. And okay, let's say we have CNT3 and CNTF as before, as the degree of contextuality for each of them. And what we know is that these measures can be formulated as linear programs whose characterization is simpler, are simpler, and the optimizations of these programs return an optimal quasi-coupling Y, for example, Y star, sorry, in the case of CNT3, and returns Z star in the case of CNTF. So here is in the scope that I presented before, we should understand this Y star that optimized the linear program for CNT3 as just this vector Y star in a relation like the one in the beginning of the presentation. So we're kind of allowing our P star to be represented in the same form of the equation, but Y star now is not a proper probability because it can have negative entries, and the degree can be measured directly to the optimal vector that we have here. We just have to get the L1 norm of the vector and subtract 1 that is the norm of a proper probability, and then you got the degree. And on the other hand, you have Z star, which again, we want to write something that's similar to that equation before, but now we are taking a vector that is subnormalized coupling. I mean, it's not a max properly because now we are allowing it to have entries that are not sum to 1. So we have Z star, and the behavior generated from it, all of it should be component-wisely be minor or equal than the entries that you have in hand with B star. Then the degree prescribed by this measure can be calculated directly from the Z star itself, which is just 1 minus the L1 norm of Z star. So we want to try to find a manner to connect these two vectors. And the way of doing this, I'm going to do this pictorially. So the idea that we got is that, okay, we can see like this Y star and Z star in the same space. This should be the space of all the factuals. I don't know if this word exists, sorry. Defecting words, the defecting vectors in the space. So here, for example, we're going to have any coupling if it falls in this region in which the sections are aligned by these blue edges, while in this part where we also have a part of the cone with black edges, we were allowing couplings with negative entries, and in this section above we have the couplings and quasi-couplings that sum to 1, while below it we have couplings and quasi-couplings that do not sum to 1, I mean, sum to something smaller than 1. And to understand the proof, as I said, we're going to need 4 steps. The first of them is to prove that we can find a Y star that carries only a single negative entry among the distributions. And the second step is to show that from this Y star, we can reach a Z star that is a solution for the CNTF LP program, a valid solution. So we're basically moving from this section above, firstly to this part of the cone of the blue edges, but in a section more above of these two. And then by modifying another entries from the resulting vector, we get into a Z star that is a proper solution for the CNTF linear program. And then with those vectors, we have 2 properties. The first of them is that the L1 norm of the difference between the Y star and the Z star that we have found are proportional to the degree of contextuality of the P star in the sense of CNT3. And this first relation is a consequence of the number of the entries that you need to modify to get that. While you have another property that is the same, L1 norm of the difference is also proportional to, is equal to the sum of the degree of contextuality in each of the senses that we have. And then the theorem follows directly from these relations. So I decided to present this in this way because I noticed that this relation in the space of couplings and so on seems like the most important thing to get in order to connect the quantifiers. So I guess that this is more important than the mathematical. I mean, I understand mathematics is important, but I'm just saying that this picture is more important to understand what's going on with the measures than I mean just seeing calculations and think that has no sense. So okay, well, so we demonstrated this theorem. So basically, have shown that all these measures are proportional in cyclic systems, and there are three perspectives to interpret the result. I guess they're kind of similar and complementary. So that are basically that the consequence of this is that the pre-order structure of behaviors in cyclic systems may be simple. I know we were suspecting that from previous works, but this is also a strong argument to say that because again, in a complement here, basically we're demonstrating that with that proportionality that a single measure seems to be needed to understand the resource in certain scenarios. So it's not like we need to study measures differently and separately in order to understand what's taking place in the scenario in the sense of the use of the resource and the structure of it throughout the structure of the correlations in the scenarios. And besides that, this is also interesting point of view that these measures are usually constructed using very different physical motivations, and this proportionality kind of promotes a connection between the physical meaning behind them. But of course, there are problems, and one of these problems that this is no longer true in other scenarios. An example of this is what they call hypercyclic scenarios that you can find in this reference here. And this, what is good about this is that this suggests that instead of looking at quantifiers and the relations between themselves, instead we should look at the structure of the behaviors themselves, like the pattern of contextuality that one can observe in a scenario, which basically means to investigate the pre-order structure of the scenario, and not look at the quantifiers like alone and the usefulness of that alone. And of course, we have caveats on our results. And the first of them is that we're treating only the cyclic scenarios, as I mentioned. And so one should consider to do similar things in order to have that main idea of a pattern of contextuality in more complicated scenarios. One should also consider the possibility of using different distance, like notions of distance to elaborate a quantifier in your system, because here we only use L1 norm. And of course, one should also consider the possibility of using measures that have a notion like that's not geometric, so like entropic ones. And for this, I guess that in our paper you can find better references on this. But basically, to consider measures that can give a different sense that the ones that geometrically one can have by investigating this kind of measures. So yeah, and I guess that is finishes my presentation. So thanks everyone. And I told you that it was supposed to be short. So any questions, please?
Thank you, Giulio, for the presentation. I have a question on the previous slide.
Okay. I mean, the right after, before that, this one?
Yes. When you say a single measure seems to be needed to understand the resource, what do you mean by that?
I mean that, we are kind of using just rulers that use different grades, but they kind of measure the same thing after all, just to give in different real numbers at the end.
Okay, so
like one is measuring like in centimeters and the other is measuring like in inches, but it's the same thing in the sense that they're proportional at the end.
okay, so this is not true for all
Mhm.
measures.
Yeah.
For a lot of them, which are the most natural ones, this is the
Mhm.
conjecture that you just finished the proof. But
Mhm.
there are quantifiers that even in cyclic systems that we know they are not equivalent. This was shown in Thiago's master thesis.
Oh, cool.
I can send it to you later if you want
Great.
to take a look at it.
Mhm.
So one question that comes from it is that how many measures we need to characterize completely the pre-order, in the sense that
Yeah.
if I know all these measures, then I know that any other that has exactly those measures has to be equivalent, in the sense that there is a
Mhm.
transformation that takes one behavior to the other and vice versa.
Mhm.
And this question was raised in a paper by the group in perimeter, the Rob Spacken's group, and which was the work that was the motivation for Thiago's work. So what Thiago did was to generalize the results that they had in that paper, which was specifically for non-locality, especially for the CHSH scenario. And Thiago generalized it for contextuality scenarios, in specific for cyclic systems.
Mhm.
And in the paper of the perimeter group, they show or they argue that you need 8 measures to characterize the pre-order in the CHSH scenario. But I'm not sure if that's correct, because the proof, because basically the dimension of the polytope is 8. So if you have
Mhm.
8 numbers, you will recover completely the behavior because of dimension 8.
Yeah.
So I think they don't take this into account. But I have to check. I'm not sure completely. Okay.
Mhm.
So maybe you needed less than 8 just to to characterize the pre-order, because you don't need to recover the behavior to characterize the pre-order. You may need less information than that.
Mhm.
So in my opinion, that is still an open question, how many you need. But we know it's
Great.
only one because of this work.
Mhm.
But I'm not sure if the answer is 8. I don't think that that the result is
Mhm.
correct.
Yeah, that's a very interesting comment, and I mean, I guess at least with this result that we had, we can basically say that I mean, if you want to look to quantifiers itself, we can basically take one of these and
Exactly.
continue from that, right?
Yes. And you know that if you need 2, you can't take all of these, because you need 2 independent,
Yeah,
and these
yeah,
they are
exactly.
all multiple of each other. And those
Yeah,
are the natural choices. So if you need more than one, you have to go for a choice that is not a natural one, at least in case.
yeah. Mhm.
But that's it. That's what I wanted to say.
Thank you. It's interesting that I mean we have these different quantifiers. For example, we have this one that allows negative entries, and the one that's I mean this the one that we use in our proof CNT3 and CNTF. One of them use negative entries, and the other is just like the portion of the system that can be recovered from a non-contextual system. And then these are kind of very different ideas, and we are showing that they are proportional. So it's just like sound as a glimpse that we need not need that much of information like the dimension of the system because exactly of that. We are not looking in one case, we are not looking at the dimension of the system themselves, and the other one we are like a totally different perspective, but these things are proportional. So like the information is the same thing. Yeah. I mean, it sounds as a suggestion that it probably need less information than that.
Yeah, but we have no idea how to prove how many units. So still an open question.
Interesting. So guys, any more questions?
Yes, Rafa wants to comment something.
Cool.
Ei, Giulio, tudo bem?
E aí? Tudo bem?
Português, right? Or English?
English.
So, Giulio, in the first slide, you wrote model-based quantum computation.
Good.
That's important. It's measurement-based, okay?
Oh, thank you. That's totally a typo. I mean, typo, no, totally aware of, this, yeah,
It's also necessary for restricted models, okay? Not for you.
Okay, I mean,
restricted like...
I use this as... Sorry.
Yes, so restricted for some specific calculation of specific functions, or it's not the... as far as I know, for the universal measurement-based model of quantum computation that uses graph states and Pauli measurements, etc., this is open question yet, as far as I know.
Oh, cool. And I guess, I mean, I used here as an example, but I guess that in this formulations of computation using just qubits, I don't know the name of the use of these, just maybe just a qubits computation, something like this. I guess this is something that's necessary also.
Qubits is really hard. It's better odd prime dimension, right?
Yeah, avoid qubits.
We avoid qubits in this case. But just wanted to mention this. I will send some other comments to you later on, okay?
Great, thank you.
More questions? Comments? So, for you that are not aware, Rafa, he was a master student in the group. He's visiting us, following Paraty. So if you want to talk to him, visit him here. He's around, okay? And he's going to speak to us on Thursday at 2 p.m. I know that it's not everyone that can, so we do exactly the same thing. We record and transmit it in Zoom. But it's going to be here, okay, in some of these rooms here. So if any of you are here in USP, we meet here Thursday, 2 p.m. Okay?
Can I ask Giulio a question?
Of course.
Certainly.
Okay, so how dependent on cycles is your proof?
How dependent on... Sorry, can you repeat this?
Yeah, on cycles, the proof, because...
the proof itself.
Yes. I know the theorems about cycles, but if you like...
So I know that one thing that is certainly particular for cyclic. I don't know if I'm right in this point, but for example, the existence of quasi-couplings and couplings, I'm not sure if it's only proved in cyclic systems, like the existence of dissolutions, but I guess if it's proved for like generic scenarios. So the existence is something important. What we use is just to find and as that first step, to use to find a quasi-coupling that has a single negative entry. So I'm trying to remember if this has something to do with cycles, and I guess it some particularity, and I guess it has because of that end that we had there. I guess that we use something like some particular relations of the entries in which we can put the negative entry and something like that, but I cannot state that for sure. But I would say that's not that much that we are using.
Yeah, because I remember the part of the proof you showed me. As far as I can tell, it had nothing to do with cycles.
Yeah.
So maybe you could prove a more general theorem like, so suppose you have a system that satisfies this condition and this one. And then in this cycle, we have your result. The quantifiers are equivalent, right? So you can maybe have a more general result already, right? So even if you don't know how to characterize these scenarios using, for instance, cycles, you can have a more general theorem right from the beginning.
Yeah, I guess that the challenge would be in the sense of generalize, basically where you can find that the one solution, the particular solution, I mean the mean of construction, the other solution, and I guess that the representation within a space would be probably messy, but it looks like possible. However, the problem is that if you look for generic scenarios, you won't usually have the proportionality. So, I mean, we have counterexamples of it, like the ones that I mentioned at the end. So, if you can find, if you aim to find a proof like in this for a more complicated scenario, uh, if there is a proportionality, you should probably expect something more complicated to elaborate, but would probably go in the same sense. However, the proportionality among all of them you should probably not expect, like in generic scenario.
Okay.
Perhaps you can think like in regions of correlations and things like that, I guess, but I'm not just speculation at this point.
Okay. Thank you.
Does this answer your question?
Yes.
Okay, thank you then.
More questions? Okay, guys, so I think that's all for today. Thank you, Giulio. And we see
Thank you, everyone.
Thursday. For half.
Great.
Thank you.
Excellent.
Or now if you're in the building.
Yeah. Bye-bye, everyone.
Bye.